Tonight we're going to explore something that sounds almost abstract, like a mathematical idea or a curious footnote in an astronomy textbook, but is in truth one of the most unsettling structures ever discovered in the universe. The Boötes Void. You may have heard the nickname before, the Great Nothing, a region of space so large, so empty, and so profoundly strange that astronomers struggled to believe it was real when it was first detected. Because the Boötes Void is not simply a gap between galaxies, it is not an unremarkable patch of dark sky. It is a cosmic cavern, an expanse hundreds of millions of light-years across, containing almost nothing at all. A region so huge that if the Milky Way were placed at its center, not a single major galaxy would appear within the visible horizon. Just darkness, silence, and the unsettling awareness of almost perfect emptiness. When you understand what the Boötes Void truly is, when you grasp its scale, how it was discovered, and why its existence challenges some of our most confident assumptions about cosmic structure, your view of the universe begins to tilt. You start to see the cosmos not as a uniform sea of stars, but as a tapestry woven from threads of matter, surrounding enormous yawning hollows where almost nothing exists. Before we dive in, if you enjoy deep-dive explorations into the mysteries of the universe and the strange, haunting structures hidden within it, a quick like or subscribe really helps the channel grow, and tapping the notification bell ensures you never miss the next journey into the cosmic unknown. Thank you. Now, let's step into the vastness. Let's begin with the thing that should not exist at all, a hole in the universe. Imagine standing on a platform suspended in the middle of the Milky Way. Around you stretch billions of stars, galaxies, and cosmic structures. Everywhere you look, the universe is busy. Clusters of galaxies forming, gas clouds collapsing, dark matter threading unseen through vast regions of space. The cosmos, for all its darkness, is never truly empty, except in one direction. There, instead of galaxies filling your field of view, you see a staggering gulf, a circular region where almost nothing exists. No clusters, no bright islands of stars, only a few scattered galaxies drifting alone in an ocean of emptiness. That region is the Boötes Void. Spanning roughly 250 to 330 million light-years across, it dwarfs everything we typically call large. For perspective, our own local group of galaxies, the one containing the Milky Way, Andromeda, and dozens of dwarf galaxies, could fit inside the Boötes Void hundreds of times over. The entire Virgo supercluster, home to tens of thousands of galaxies, would disappear inside it like a grain of sand dropped into a canyon. Galaxies are not rare in the universe. In fact, they cover the cosmic landscape in elaborate patterns, forming filaments, walls, and clusters. So when astronomers discovered a region that should statistically host tens of thousands of galaxies, but contained barely more than a few dozen, it was as if a spotlight had carved out the sky. The Boötes Void is not empty because it lacks matter in the usual sense. It is empty because it defies the natural expectation of how galaxies should spread across space. It is a hole in the cosmic web, a vast, silent chamber of the universe where the lights simply never turned on. And the closer you look, the stranger it gets. Human minds are not built to grasp distances measured in millions of light-years. Even scientists struggle to express the vastness of the Boötes Void without reaching for metaphors or comparisons. So let's visualize it in a way that captures both its immensity and its eerie lack of structure. Imagine shrinking the Milky Way down until it's the size of a single grain of sand. Now imagine placing that grain inside a sphere the width of the entire Earth. Even at this scale, the Boötes Void would still be empty. No other grains, no clusters, just a few isolated specks separated by horrifying expanses of nothing. Or picture the cosmic web, the universe's large-scale structure, like a three-dimensional sponge made of glowing filaments. Galaxies cling to the strands, clusters gather at intersections, and between them lie pockets of lower density. But voids are typically modest, dozens of millions of light-years across. The Boötes Void is not modest. It is a tear in the sponge, a spherical region where the filaments barely touch, as if the cosmic web simply forgot to weave itself there. Astronomers estimate that the void contains more than 250,000 times the volume of the Milky Way galaxy. It is so large that if humanity could travel at the speed of light, crossing its diameter would still take longer than the entire history of complex life on Earth. And yet, buried inside this immensity are only a handful of lonely galaxies, not arranged in patterns, not gathered into clusters, just isolated wanderers drifting through the dark. The Boötes Void is not a structure you can simply map. It is a structure you have to feel, a scale that presses against the limits of human comprehension. The Boötes Void came to light by accident. In 1981, astronomer Robert Kirshner and his team were conducting a galaxy redshift survey, mapping the distances of galaxies to understand how matter clusters on large scales. These surveys reveal the cosmic web, galaxies arranged like beads along threads of invisible dark matter. But when Kirshner plotted the redshift data from the Boötes constellation, a strange pattern emerged. There were gaps, not small gaps, not empty patches explainable by dust or instrument error. A colossal region, hundreds of millions of light-years across, contained almost no galaxies at all. At first, the team thought it must be a statistical anomaly or a sampling error. Perhaps the data was incomplete. Perhaps they had accidentally mapped a direction obscured by gas clouds. But further surveys confirmed the result. The void was real. Its size was so far beyond expectations that astronomers struggled to understand how it formed. Standard cosmology predicts voids, but nothing this large, nothing this empty, nothing this abrupt. Even today, the Boötes Void stands as one of the most extreme supervoids ever discovered, a cosmic hollow that pushes the limits of our models, our assumptions, and our understanding of how galaxies arrange themselves across the universe. A sphere of near emptiness, suspended in the night sky, a structure that raises more questions than it answers. To understand how the Boötes Void was discovered, we need to step into the world of cosmic cartography, mapping a universe so vast that even light, the fastest thing we know, struggles to cross it. Astronomers don't navigate the cosmos the way explorers once charted oceans or continents. Instead, they map space by measuring how galaxies move away from us, using a phenomenon called redshift. As the universe expands, the light from distant galaxies stretches into longer wavelengths, shifting toward the red part of the spectrum. The farther a galaxy is, the more its light is redshifted. By measuring this shift, astronomers can determine how far away a galaxy lies, placing it in a three-dimensional map of the universe. When enough galaxies are measured, large-scale structures begin to emerge: walls, filaments, clusters, and the vast voids between them. In the early 1980s, these maps were still in their infancy. The technology was limited, surveys were painstaking. Each redshift took time, patience, and equipment far less sophisticated than the tools we have today. But even with these limitations, astronomers began to notice patterns. Galaxies were not scattered randomly. They gathered in intricate webs, forming a structure that looked almost organic. And then, in the Boötes region, the map revealed something extraordinary. A shape appeared, a bubble of emptiness, a sphere in which galaxies were conspicuously absent, creating a region so devoid of structure that it looked like someone had carved a hole out of the universe itself. This was not an artifact of measurement. The absence persisted no matter how the data was checked, no matter how new observations were collected. The Boötes Void became one of the first major confirmations that the large-scale universe is not uniform. It is patchy, lumpy, textured, defined as much by what isn't there as by what is. Astronomy had always assumed the universe was evenly filled. The Boötes Void proved otherwise. When the Boötes Void first appeared in redshift maps, astronomers were confronted with what looked like a statistical impossibility. The distribution of galaxies in the universe typically follows predictable patterns. Some regions host clusters or filaments, others contain smaller voids, but nothing approaches the scale of the Boötes Void. Its absence of galaxies was so extreme that the earliest models struggled to explain how such a structure could have formed naturally. On the redshift diagrams, where each dot represented a galaxy, normal regions showed dense clusters or branching filaments. But the Boötes region appeared as a blank expanse, a vast sphere in which dots were almost entirely missing. Only a few galaxies dotted the void, like solitary lights floating in a vast ocean of darkness. To put this into perspective, based on average galactic density, the Boötes Void should contain more than 10,000 galaxies. Instead, it holds roughly 60. This is not a small discrepancy, it is a profound anomaly. Such a vacuum could not be explained by observational gaps or by instruments failing to detect faint galaxies. The void was simply too large and too deep. If the universe were a painting, the Boötes Void would be the place where the brush never touched the canvas. As researchers analyzed the structure further, they realized the void also exhibited sharp boundaries. It was not gradually thinning out, as would be expected if galaxies simply became sparse. Instead, the edges were abrupt, as though something had carved out a spherical region and left the rest untouched. The Boötes Void wasn't just empty, it was structured emptiness, and that made it far stranger than a random fluctuation in the cosmos. When astronomers look at the distribution of galaxies across the universe, they often rely on probability and statistics to understand why certain regions contain more or fewer galaxies than others. Some variation is expected. Small voids occur naturally. Larger voids are rarer but still within the realm of chance. But the Boötes Void sits far outside these expectations. Its size alone positions it at the extreme end of cosmic structures, but its combination of size and depth, both immense and almost entirely empty, is so improbable that random chance cannot account for it. The odds of such a region forming purely by statistical fluctuation are effectively zero. Simulations of large-scale cosmic structure formation reinforce this. When scientists model the universe using known physics, gravity, dark matter, dark energy, and the standard framework of cosmology, they can produce voids, walls, filaments, and clusters remarkably similar to what we observe. Yet even in the most extreme scenarios, voids like Boötes are exceedingly rare, and none reach its dimensions with such profound emptiness. Its existence implies something happened during the early stages of the universe's formation, something beyond the ordinary interplay of gravity and expansion. Perhaps smaller voids merged, perhaps dark energy behaved differently in certain regions during the cosmic dawn, or perhaps massive gravitational structures on the void's periphery influenced its evolution, sweeping matter away over billions of years. Regardless of the mechanism, one thing is clear. The Boötes Void is not a cosmic accident. It is a deliberate feature of the universe's architecture, one that challenges our understanding of how galaxies, matter, and the unseen forces of the cosmos arrange themselves across unimaginable distances. To understand why a void like Boötes can exist, we must explore the universe's underlying architecture, the cosmic web. On the largest scales, matter in the universe does not spread evenly. Instead, it forms a colossal, interconnected network shaped by gravity and dark matter. Galaxies cluster along threads, meet at intersections, and gather into immense superclusters. Between these structures lie pockets of lower density, voids. These voids are not mistakes or gaps, they are essential components of cosmic geometry. When the universe was young, just hundreds of thousands of years old, tiny fluctuations in density were imprinted onto the cosmos. Over billions of years, gravity amplified these fluctuations. Regions with slightly more matter collapsed into filaments and clusters, while regions with slightly less matter stretched into cavities. Under typical circumstances, these cavities grow into voids tens of millions of light-years across. They expand slowly, pushing galaxies toward the denser edges of the web. But the Boötes Void pushes this concept to an extreme. It is not a simple cavity, it is a supervoid, a sphere so immense that it appears to be the result of multiple voids merging, compounding their emptiness into one overwhelming expanse. In cosmic simulations, such supervoids can form, but they remain rare. They require fine-tuned initial conditions, regions where the primordial density was exceptionally low, where dark matter was sparse, and where surrounding structures grew disproportionately dense. Over billions of years, gravity pulled matter away from the region, leaving behind a vast hollow. The Boötes Void is not merely a hole in the cosmic web. It is a vast ancient imprint, frozen testimony to the universe's earliest moments, when the cosmic architecture was first being carved into shape. One compelling idea for the Boötes Void's formation lies in the dynamics of cosmic bubbles, regions of space that expanded differently from their surroundings in the early universe. During the first fractions of a second after the Big Bang, fluctuations in energy density could have caused certain regions to inflate more rapidly, leaving them with fewer seeds for galaxy formation. In this framework, the Boötes Void may be the result of inflation sculpting a massive underdense region, one that later expanded into a true supervoid. As the universe aged and dark energy began to dominate cosmic expansion, these underdense regions may have grown even more pronounced. With less gravitational pull to counteract expansion, a void can stretch wider and faster than its denser surroundings. Another explanation suggests that the Boötes Void is not a single structure at all, but rather a conglomeration of smaller voids, a chain reaction collapse of low-density pockets. As these smaller voids merge, they create a larger, nearly spherical cavity. Galaxy surveys reveal that the Boötes region contains substructures and faint hints of past divisions, supporting the idea of multiple voids coalescing into one grand emptiness. Some researchers have even proposed gravitational influences from surrounding superclusters, structures so massive that their combined pull could have drained matter away from the void over cosmic time. In this scenario, the Boötes Void resembles a bubble pressed outward by the mass of its neighbors, its interior stretched thin as galaxies migrate to denser regions. Whether forged in the turbulence of the early universe or sculpted slowly over billions of years, the Boötes Void embodies the silent power of cosmic evolution. It is a reminder that emptiness is not passive. It grows, stretches, and reshapes itself as the universe expands. Although the Boötes Void resides far from our local cosmic neighborhood, it exists within a larger gravitational environment shaped by massive structures, including the enigmatic Great Attractor. This gravitational anomaly, located hundreds of millions of light-years away, influences the motion of entire galaxy clusters, including our own. Its immense pull hints at concentrations of matter far greater than anything in our immediate vicinity. While the Great Attractor is not directly responsible for sculpting the Boötes Void, its presence helps illustrate how gravitational forces across vast distances shape the distribution of galaxies. The cosmic web is not static. It warps, stretches, and shifts under the influence of dense regions. Matter flows toward these gravitational wells, leaving behind underdense pockets that grow emptier over time. Some theories suggest that the Boötes Void may have been influenced by the surrounding landscape of superclusters, the Hercules supercluster, the Corona Borealis supercluster, and others that form a complex gravitational environment. While none exert enough force individually to carve out the void, their combined mass may have contributed to a gradual siphoning of material, enhancing the void's expansion and maintaining its remarkable emptiness. This interplay between dense regions and empty ones underscores a profound truth. The universe's grand design is written not only in the places where galaxies cluster, but also in the regions they abandon. Every void is shaped by what surrounds it. Every supercluster leaves a long shadow across cosmic distances, subtly drawing matter away, deepening the hollows, and sharpening the boundaries of emptiness. In this context, the Boötes Void becomes more than an anomaly. It becomes a marker of how gravity, dark matter, and cosmic expansion collectively sculpt the universe. One region of profound silence balanced against the weight of colossal structures elsewhere. The existence of the Boötes Void forces astronomers to confront questions that cut to the heart of cosmology. In a universe governed by gravity, filled with dark matter scaffolding, and seeded by early quantum fluctuations, such an enormous region of near emptiness is not merely unusual, it is diagnostic. It reveals something crucial about how the cosmos grew from its earliest moments to its present structure. One of the key lessons is that emptiness is as fundamental to the universe as matter. Superclusters, galaxy walls, and filaments are spectacular, but they are only one half of the cosmic architecture. The voids, places where gravity had little to work with, tell an equally important story. The Boötes Void, in particular, highlights how dramatically different regions of the universe can become based on the slightest variations in their primordial density. Its sheer size challenges the idea of uniformity on the largest scales. Standard cosmology assumes that the universe is roughly homogeneous when viewed broadly enough, but a supervoid like Boötes pushes that assumption to its limits. It is a reminder that cosmic evolution does not proceed evenly across space. Instead, it is shaped by local conditions that ripple outward over billions of years. The void also underscores how incomplete our understanding of dark matter and dark energy truly is. These invisible components dominate the mass-energy content of the universe, guiding the formation of structure. Yet regions like Boötes reveal gaps in our models, places where predictions fall short and where nature surprises us with unexpected extremes. In this way, the Boötes Void becomes an enormous clue, a silent, lightless region offering insight into how the cosmos distributes matter, how gravitational instabilities deepen, and how the early universe set the stage for everything we see today. To understand why the Boötes Void is so empty, we must grapple with the invisible forces that shape the universe's large-scale structure. Dark matter, though unseen, acts as the gravitational framework on which galaxies form. Dark energy, still mysterious, drives the accelerating expansion of the universe. Together, they do far more than simply influence cosmic evolution. They define it. In ordinary regions, dark matter forms dense halos that attract gas, allowing galaxies to grow. But in underdense regions, dark matter is scarce. Without this scaffolding, galaxies struggle to form. The Boötes Void may be a prime example of such an environment, a place where dark matter density was simply too low to support normal galaxy formation. Dark energy plays its own role. In empty regions where gravity is weak, cosmic expansion has less resistance. As a result, voids expand faster than denser areas. This accelerated growth can magnify minor differences in density, transforming a modest underdensity into a massive supervoid. Over billions of years, the Boötes region may have been stretched wider and thinner, its interior evacuated of matter as expansion outpaced gravitational attraction. The interplay between dark matter and dark energy is subtle but profound. In regions where both align toward emptiness, voids grow faster, deeper, and more pronounced. Simulations suggest that supervoids like Boötes can only emerge when these invisible forces combine in extreme configurations, conditions that might have been set during the earliest epochs of cosmic inflation. For astronomers, studying such voids offers a rare opportunity. The Boötes Void acts almost like an experimental chamber in space, a place where the usual rules of structure formation weaken and the underlying physics becomes clearer. By examining how galaxies behave at its edges, how light moves through it, and how matter is distributed inside it, researchers can test models of cosmic evolution with greater precision. In the darkness of the Boötes Void, the invisible universe reveals itself. As telescopes grow more powerful and surveys more detailed, our understanding of cosmic voids continues to evolve. Instruments launched in the mid-2020s, like the James Webb Space Telescope, ESA's Euclid mission, and next-generation ground-based observatories, are mapping the universe with unprecedented depth and clarity. They allow astronomers to peer deeper into voids, detect faint galaxies that earlier surveys missed, and refine the contours of these colossal structures with extraordinary accuracy. For the Boötes Void, this means the picture is still sharpening. More galaxies may be discovered within it, though their scarcity will remain extreme. The void itself may prove even larger or more complex than early measurements indicated. Some researchers suspect it may connect to other underdense regions, forming vast chains of emptiness rivaling the size of known superclusters. Yet the most tantalizing question is whether the Boötes Void is unique, or simply the first extreme example we happen to notice. As all sky surveys expand, astronomers are revealing increasingly large and intricate voids scattered across the cosmos. Some may eventually surpass Boötes in size or depth. Others may possess shapes and boundaries even more puzzling than a near-perfect sphere. Each discovery adds a new piece to the puzzle of cosmic structure. Each void deepens our understanding of how the universe organizes itself on unimaginable scales, and each new map challenges our assumptions about what should and should not exist. The Boötes Void remains one of the universe's most haunting features, a silent, lightless expanse that stretches the imagination to its breaking point. It is a reminder that the cosmos is not just made of stars, galaxies, and brilliant structures, but also of vast chasms where creation never took hold. In its emptiness, the Boötes Void speaks. It tells us that the universe is stranger, more varied, and more layered than our models can yet fully capture, and it invites us to keep exploring, keep mapping, and keep listening to the quiet spaces where the cosmos reveals some of its most profound truths.